everyone, thank you so much for clicking onto the video. Here are today's learning objectives. So the first is to know the number of electrons that can fill the first 4 quantum shells, and then to know that an orbital is a region within an atom that can hold up to 2 electrons with opposite spins, and then to know the shape of an s orbital and a p orbital. We're then going to look at the number of electrons that occupy sp and d subshells, and to know that electrons fill subshells singly before pairing up, and that 2 electrons in the same orbital must have opposite spins. We're then going to be able to predict the electronic configurations using 1s notation and electrons in boxes notation of atoms given the atomic number Z up to Z equals 36, and ions given the atomic number Z and the ionic charge for S and P block ions only up to Z equals 36. And finally, we're going to know that elements can be classified as SP and D block elements. So now we're going to talk about electron arrangement. And electrons are arranged in energy levels, or electron shells, which we've seen before at GCSE. And these energy levels actually have subshells. And we have the existence of S, P, D, and F subshells. And each one of these subshells then consists of electron orbitals. And orbitals are just regions of space where electrons are likely to be found. Each of these orbitals has a number, and this tells us the main energy level, so the electron shell that it corresponds to. So for example, if it's in the first energy level, or the first electron shell, then it'll have a number 1, and then we'll have 2 for the second main energy level, and so on. And so we can use an energy level diagram to represent atoms and their electron shells. So here we have an energy level diagram. So on the y-axis, we've got energy, and on the x-axis, we've got the distance from the nucleus. So for example, looking at 1s. 1s is the first shell because it's got number 1. And so that's why it's the closest to the nucleus. Because if you think back to GCSE, we have the nucleus, and then we have the first shell of electrons around the nucleus. And so it's the closest to the nucleus. And we also find that if we go further and further out, so when we get to higher and higher main energy levels, the energy increases. So for example, the 4th shell will have a much higher energy than the first shell. And so quickly running through subshells and the orbitals. For the first main energy level, we only have one subshell, and that's the S subshell. And the S subshell consists of one orbital, which is the S orbital. And then the second shell, we have 2 subshells. So we have the S subshell and the P subshell. And the S subshell comes as 1 orbital, and the P subshell comes as 3 orbitals. And then for the third shell, we have the S and the P again, which is exactly the same. And then we also have an added D subshell, and this is split up into 5 different orbitals. And then for the 4th shell, we then have an added F subshell, which then has 7 orbitals. So quickly summarizing that, what the number represents is the main energy level. Which is basically the electron shell. And then we have the letters S, P, D, and F, and these are subshells. And then if we look at an individual box like this one, what we call this box is an orbital. And so now we're going to look at how to fill out these energy level diagrams. So firstly, we need to look at a few rules, and this will help us first fill the diagram out. So the first rule is that electrons are filled into the lowest available energy level first. And then electrons prefer to occupy orbitals on their own. And one really, really important rule is that 4s fills and empties before 3d. And this makes sense because we know that electrons are filled into the lowest available energy level first. And if we look back at the energy level diagram, the 4s orbital is actually of a lower energy than the 3d subshell. And so that's why 4s gets filled out before the 3d subshell. And then finally, any single atomic orbital can hold a maximum of 2 electrons, and they have to have opposite spins. And what we mean by opposite spins is that one will spin clockwise, whilst the other one will spin anti-clockwise. So, for example, if we look at how to fill out the energy level diagram for silicon, the first thing we do is look at the periodic table and see how many electrons silicon has. And it actually has 14 electrons, and so that's how many we need to fill out. So using the first rule, we need to fill the electrons into the lowest available energy level first. So the lowest available energy level in this case is the first shell, because we don't have any electrons yet. And so we can fill out 2 for this 1s orbital. Because you might think, because electrons prefer to occupy orbitals on their own, that this second electron would go into 2s. But this rule is actually overridden by the first one, because electrons are always filled out into the lowest available energy level first. And so we've now filled out 2 electrons, and so now we fill out 2s. So we have another 2 electrons, and I draw them like this because this indicates the spin. So we have one which is spinning, let's say, clockwise, and the other one which is spinning anti-clockwise. And then we fill out 2p. So now we need to remember our rule about how electrons prefer to occupy orbitals on their own. So we fill out 3 separately first. So we have 1, 2, and 3. And then we can fill out the next 3. So we have 1, 2, and 3. So now we fill out 10, so we need 4 more. So we fill out 3s with 2 electrons. And now we need another 2 electrons. And so now we need to remember about how electrons prefer to occupy orbitals on their own again. So we need 1 in this orbital and a second one in this orbital. So this is our finished energy level diagram for silicon. However, if we were going to look at something like calcium, so calcium has 20 electrons. So we're looking at calcium, and it has 20 electrons. So right now we've filled out 14, so we need 6 more. So if I continue this energy level diagram, we should be able to get the energy level diagram for calcium. So add another 1, and then we add another 3 like we did for the 2p subshell. So now we have an added 4, and now we need 2 more. But now we need to remember our rule about how 4s will fill before 3d. And so we need to fill out 2 electrons into 4s instead of any in the 3d. And so this would be our energy level diagram for calcium. And we can also write out the electron configurations of atoms without using a diagram, so a shorthand method. And so, for example, we're going to look at how to write out the electron configuration of calcium. So calcium we've just seen, and we've just drawn on the energy level diagram. And so we can just take that and convert it into a shorthand way of writing it. So we have 2 electrons in the 1s orbital. And so what we do is we have 1s, and then we put in a 2, which just indicates that we have 2 electrons in that orbital. And then we have 2s, and we also have 2 electrons, and so we put number 2 there. And then we have our 2p subshell, and instead of writing out all the orbitals, we just write out the subshell. So it has 6 electrons in the total subshell, so we have a 6 on top of the 2p. And then we have 3s, which has another 2 electrons. And then we have 3p, which has 6 electrons. And then we have 4s, which has 2 electrons. So like the energy level diagram, we miss out the 3d. So this is our electron configuration for calcium. And now we're actually going to look at what this kind of means on a periodic table, so what the relationship is. So going to the periodic table, we can actually split this up into blocks. So if we look at this block here on the left, and if I split it off like this and draw it into a rectangle, this block is what we call the S block. And what that means is just that the outer electrons are in an s orbital. And then we have the block in the middle, which is all the transition metals. And this block is what we call the d block. So all of their outer electrons are in a d orbital. And then finally, on the right-hand side, we have the p block. So if I split it up like this is what we call the p block. So all of their outer electrons are in a p orbital. And actually, hydrogen and helium are both in the s block as well. And how we get this number in front, so the energy level, or the electron shell. So for example, here we have 2. How we get this 2 is this is actually the period number. So it's the number of the row. So for example, we have lithium here, and this is an s block, so we know that the outer electron is in an s orbital. And it's also in period 2. So that means that the outer electron must be in a 2s. And so the electron configuration for lithium is actually 1s2 and then 2s1. So for hydrogen, we have 1s because we fill out the 1s orbital first, and we have 1 electron. And then for helium, we would have 1s2 because we can fit 2 in this 1s orbital. And then we start to fill out the 2s orbital, and that's why lithium is 1s2, 2s1. So for example, if we wanted to work out, let's say krypton here, instead of counting all the way across the periodic table, we can simply work this out by just looking at the block and the period it's in. So it's in the p block, so that means that the outer electron is in a p orbital, and it's also in period 4, and so the outer electron must be in a 4p orbital. So the electron configuration for krypton is 1s2, 2s2, 2p6, 3s2, and then we have 3p6, and we have 4s2, so we need to remember that that comes first before the 3d, and then we have 3d10, and then we have 4p6. And how we know it's 4p6 is because the p block for period 4 starts with this gallium. And so counting along, we have 6 until we get to krypton. Because gallium would be 4p1 because it's the start of the p block. And then germanium would be 4p2, arsenic would be 4p3, and so on. And so that's why krypton would be 4p. And there's actually 2 really, really important exceptions that we need to look at. And those are chromium and copper. So firstly, if we look at chromium, which is here on the periodic table, it's in the d block, and it has 4 electrons in a 3d orbital. So what we would expect it to be would be 1s2, 2s2, and then 2p6, 3s2, 3p6. So this would take us to argon, and then we'd have 4s2, and we'd expect it to be 3d4. However, this isn't the case because chromium likes to only have 1 electron in the 4s, and this happens because of the closeness of the 4s and 3d subshells. So instead of having this, so this is wrong, we have 1s2, 2s2, 2p6, 3s2, 3p6, and then we have 4s1. So only 1 electron is put into the 4s orbital. And so that means that we would have to have 3d5 to account for that extra electron. And then looking at copper, we have a similar thing. So copper is here, and so we would expect 9 electrons in this 3D orbital. So we have copper is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. However, this is wrong again because copper is also an exception and it likes to have 1 electron in its 4s orbital instead. And so what we have is 1s2, 2s2, 2p6, 3s2, 3p6, 4s, and then 1, and then 3d10. Because again, we have an extra electron that we'll need to put in the 3D orbital. And also something really important to notice is that even though I said that you could work out using the period which main energy level the electrons are in, well, the outermost electrons are in, it's not entirely true, because if we look at the D block, the first period of the D block is actually in group 4, but those electrons, those outer electrons are in the 3D orbital, like we have for chromium and copper. And so for the D block, we always have to -1 from the period to find which main energy level the outer electron is in. We also need to look at electron configurations for ions. So the general method we have is that we write the electron configuration for the atom and then take off or add on any electrons depending on the charge. And then the third rule is that we need to remember that 4s fills and empties before 3D. So for example, if we're going to write the electron configuration for the O2- ion, firstly what we do would be look at the periodic table and write the electron configuration for oxygen. So oxygen is in period 2 and it's in group 6. And so we have 1s2, which takes us to helium, and then 2s2, which takes us to beryllium. And then we have 4 more electrons, so then we have 2p4. And then because it's a 2- ion, this means that we're adding 2 electrons. So what we have is that for O2-, we have 1s2 and then 2s2. But because we've added 2 extra electrons, we actually now have a full 2p orbital. And that's the whole point of forming these ions, because they all want to get a full outer shell. So we have 2p6, and this is the electron configuration for O2-. And then the second example we're going to look at is the electron configuration for the chromium 3+ ion. So firstly, looking at chromium, we need to remember that this is an anomaly because it likes to have 1 electron in the 4s instead of 2. So we have 1s2, 2s2, 2p6, and then 3s2, 3p6. So this brings us to argon. And then 4s fills before 3D, so we have 4s, but it likes to have 1. So we have 4s1 and then 3d5. So this is chromium. And then because we have a 3+ charge, that means we're removing 3 electrons, because electrons are negatively charged. So if the charge is going from 0 to +3, we must be removing 3 electrons. And so what we have is that for this chromium 3+, we have 1s2, 2s2, 2p6, 3s2, 3p6, and now we need to remember that 4s will empty before 3D. And so we've emptied this one here, so this one is not here anymore, and then we need to remove 2 from this one. So then what we get is 3d3. So now we're going to look at shapes of orbitals. Now the atomic orbitals of each main level that we've looked at have different shapes, and these all have slightly different energies. And they're described by the letters S, P, D, and F. And these shapes represent a volume of space in which there's a 95% probability of finding an electron. And this is what influences these shapes of molecules. So first we have an s orbital, and an s orbital has this spherical kind of shape. And then for the p orbital, we have a shape which we call a dumbbell. And another thing we need to know is that the main levels can also be called quantum shells. So, for example, the first shell, so the first electron shell we have, is also the first quantum shell. And how we denote a quantum shell is we say n equals 1. So we need to know how many electrons there are in each quantum shell. So for the first quantum shell, n equals 1. So if we think about it, we have 1s2. And so we must have 2 electrons in this first quantum shell. And then looking at n equals 2, we have 2s2 and 2p6, so we must have 8 electrons. And then for the third quantum shell, we have 3s2, 3p6, and 3d10. So that would be 18 electrons. And then for n equals 4, we have 4s2, 4p6, 4d10, and also 4f14, because we can have 7 of these f orbitals. And so we have 32 electrons in this fourth quantum shell.